Good morning.
Morning.
How are you?
I'm fine.
Have you been able to get onto the Jupyter Hub and use it successfully?
No, I haven't.
You haven't yet? Okay. Is
No,
there,
I haven't.
have you tried recently?
I'm having a internet connectivity.
Oh, okay. So you're not able to access the internet at all?
Yes.
Hmm.
I'll do that.
Okay, well, yeah, if you can give it a try, let me know, because I think hopefully you have access and then you can run everything yourself. Adams just asked if you can use the data sets for research purposes toward publication. So yes, so these data sets that are on the cloud are available for anyone to look at and anyone to use. You just cite it in your paper or presentation. But that's kind of the goal of putting them on the cloud like this, is so that we can all access them. And there's so much information coming out of these data sets and models and observations. Yeah, the people who make them really want people to use them and analyze them. So you can absolutely use these data sets for research. Okay, I will start sharing my screen. Pull up the chat. Okay. And okay, so let's see how far we get through. So as usual, I'm starting my session by showing the schedule, because all the information that you need for the week, hopefully, is in this document. So to get to the Jupyter Hub or to see anything related to the session that you want, we're doing this session now. This is Thursday, July 29th. And we can click on this ECCO Python tutorial, and it takes us to this page with all of the ECCO information. So if you haven't yet, I do encourage you to watch this pre-recorded lecture. It kind of is an overview of what ECCO is. So it stands for Estimating the Circulation and Climate of the Ocean. And this YouTube link here, along with the slides, is a talk about kind of what ECCO is. So I won't go into that too much, but we'll get a little taste of what it is by going through some of these notebooks today. Here's the lab that we're doing. We'll be doing this today. So here's the link to the Jupyter Hub. If you haven't filled out the Google form yet, hopefully you have, but if you haven't, there's the link. These are the tutorials that you're attending now. And then there are Q&A sessions with Dr. Dimitri Menamenlis. He is a real guru on everything ECCO. So if you have any interest in ocean modeling or ocean science or anything like that, he's the person to ask. So I really encourage you to attend that. So there's one this week, which I think a couple of you attended, and there's another one next week. So we added this to the schedule. This is new. So next Tuesday, there's an added session, and there's a Slack channel here to follow along. Okay, so we click the link to the Jupyter Hub and we log in using our Google account, and we should get to a page that looks like this. And hopefully all of you are familiar with kind of the Jupyter Lab layout from the previous sessions. As always, you can stop and ask questions as we go, or type them in the chat, whichever you prefer. So today I'm going to start with this intro Xarray and dask notebook. So I double click that here and it opens up on the right. So yesterday's session, so I guess just a reminder that in Python, we have to load libraries that we want that have the functionalities that we want. So in yesterday's session, for instance, which I think several of you were there, we used the pandas library, which is really good for using for loading and manipulating and analyzing tabular data. So data that kind of fits in a table that you'd put in Excel. It's very, very commonly used. Xarray is a different package. It's a different Python package that basically extends Pandas functionality to multiple dimensions. So whereas when you have a table, you kind of have your y-axis and x, so you've got rows and columns. In Xarray, you can have many dimensions. So you can have rows, columns, but you can also have, like a third dimension or a fourth dimension. It gets hard to visualize, but it's a really nice way for handling multidimensional data. And that's very useful for a lot of climate scientists and ocean scientists because a lot of our data sets come in many dimensions. So for instance, it's very common in an ocean model or ocean observations that you have two horizontal dimensions. So you have your latitude and you have longitude, but then you also have depth of the ocean. So that's a third dimension. But then you have all of that at every point in time. So time is kind of like your fourth dimension. And so Xarray is much easier for handling that kind of data compared to like Pandas. So that's why we're going to talk first just about the basics of Xarray. Dask is something that is used, it's another Python package. It's used often in conjunction with Xarray. In fact, they work together. And it is very handy for dealing with large data sets. So large can have different meanings, but basically once you get to many gigabytes, when it can be a bit harder to load in to your computer, then that's kind of when it's large. And they can get very large. So they can get to petabytes, terabytes. So it can be quite large. So Dask is really useful for that. Okay, looks like we have a few more people joining. Are there any questions about what I've said so far and what we're planning to do today? Okay. So I will be kind of diving into all of this and hopefully you can kind of keep up. I know a lot of this is probably gonna be very new to many of you. So do ask questions, but I'm going to kind of forge ahead and hopefully you can see it and it'll start to make sense, even if you have to go back and kind of read everything here and look up these other resources. So Xarray fundamentals, if you're really interested in Xarray, if you're dealing with data that is multidimensional like this, or you're interested in it, this is a really good resource. This is from Ryan Abernathy, and he did a research computing course, and he has a notebook here on Xarray fundamentals. It's really great. Similarly, he has a resource here for dask. So I'm going to go into the very basics, but he goes into a bit more detail. And this is again part of his research computing class. Sorry, I'm just getting a bit of noise. So if I mute you, it's just I'm getting background noise, but you are welcome to unmute and ask a question at any time. Okay, there's a question in the chat. Can Xarray be used in place of Arakawa's grid? Okay, that's a good question. So the grid of the model is very important. So, and you're right. So the Arakawa grid is often used in climate and ocean models. And you have like an Arakawa B grid and a C grid. ECCO uses an Arakawa C grid, which I will mention a bit later. So Xarray does not replace the grid of the model. So that's separate. So Xarray is more about handling the actual data itself, not the grid that it's on. And as we go through, I think that will become more clear. So in an Xarray data set, you will have all of the dimensions irrelevant of the actual grid. And you'll have lots of coordinates as well. And I'm getting a little ahead of myself, but we'll kind of see how everything is packaged together in Xarray. So I might answer that question a bit later, if that's okay. All right. So if there are no other questions, I will start here. And I remember like when I zoom in. Okay, so first we're going to start by loading a data set from the cloud. And this is the code that we can use to do that. This is loading the CESM POP model. So this is the Community Earth System model. And POP stands for Parallel Ocean Program. I think it's program. And so it's the ocean portion of this climate model. And this is just an example. So I mentioned this in a previous session, so I won't go into it now, but this code, like these lines of code here, can be found in the Pangeo data gallery. So you can just look up there what data set you might want to look at, and it'll tell you what code you should copy and paste into your program so that you can load the data set. So that's all I did here, is I just copied that and I hold down Shift and press Enter. We see the little star over in the corner of the cell. That means it's working. There we go. And now it says 1, which means it evaluated. So I have now loaded my data. However, what I mean by loaded the data is actually a bit different than in yesterday's tutorial when we loaded a data set from the shared folder here. And that's because this data is really big. We'll take a look at how big some of these are later, but it's many terabytes, which is a lot of gigabytes. So we can't actually load all this data into memory. It's just way too big. So what I've just done, and what Xarray allows you to do, is to load just the metadata, which is kind of all of the information about the data set, which is really all that you want initially. So if you notice here, I create this variable called ds, which is short for data set. And I use this, you don't really need to know this here, but just using this, calling this cat, which is what we defined here, which is this catalog. So you're basically saying, open this from the catalog. And so I've defined our data set to be ds. So if I shift return in this cell here, then it will print out what ds looks like. So ds, or this data set, can be represented like this. So this might look a bit familiar to, like it's kind of similar, it looks different, but it's a similar kind of graphical interface that we had in the pandas library yesterday when we could see the table with all of the rows and all of the columns. This is as good as we can do when we have multidimensional data. So we can't visualize all of the different dimensions now. It's not just 2 dimensions like our table was, but we can still take a look at what is in the data set. So, and we see at the top here, this is what type the data is. So it says this is an Xarray data set. I can zoom in more. So that's what type our data, that's what DS is. DS is an Xarray data set, and that's just what it's called. And in the data set, we have several different items. The first of which is dimensions. So dimensions are things like latitude, which is what nlat is. Nlon is our longitude. So these are the literal dimensions of the data set. So you've got longitude, latitude, you have time. Oops. You've got time here. And then you have a few, actually quite a few different dimensions that say Z underscore something. So Z underscore T, Z underscore T underscore 150 meters. We don't have to worry about the details right now because this is just a sample data set, but Z is basically our depth variable. And there are just quite a few of them for different reasons. So these are all of the dimensions in the data set. So that's really nice that we can view what dimensions there are. Next up is these coordinates, and you can see this number 59 in parentheses. That means that there are 59 coordinates in this data set. So if I click here, then you can see it, the arrow goes down and it shows all of the coordinates that are listed in our data set, and there are 59. That's why it took so long for me to scroll by. So coordinates are things like for instance, we have this dxt coordinate here. It's a 2-dimensional coordinate, so it's latitude by longitude. And if we go over on the right here, we can click on this little paper icon, and it will tell us what dxt is. So it says long name : x spacing centered at t points. So there's a lot of jargon here, which for now we don't need to know specifically. We'll be looking at this more specifically in the ECCO dataset. But the T points refers to what points on the Arakawa grid, which Ogunseititis, sorry if I hope that's close. Please correct me if I'm wrong. But that's what you were mentioning, the Arakawa grid. And that's where you have different, well, I'll show that in a second, but you have different points. So this is saying, this is like the space between the points in the X direction or in the longitude direction. And it also gives us the units. So it says this is in centimeters. That can be really useful. I don't know about all of you, but I know some very famous examples of where people didn't know what units they were and got something wrong. So you had centimeters, but you thought you had meters or something. So anyway, this is really nice. You can click that paper icon again, it'll go away. You can also click this cylinder here, and it will show you kind of a visual representation of this coordinate in this case. So it tells you how big it is. It's 69 megabytes. So this coordinate is quite small. And it says it's only 2 dimensions. And so in the X dimension, it's 3,600, and then you got 2,400 in the Y dimension. So that's just a nice way to visualize. Okay. Scrolling down, we get the next thing here we have is these variables. So there are 12 variables, and they are all listed here. So these are the things that we're usually most interested in doing analysis on. Things like coordinates can help us do the calculation to get there, but often we might be interested in, for instance, sea surface temperature, which would be SST. We can see here that SST has 3 dimensions. So it evolves in time, as well as latitude and longitude. And if we go over to the right-hand side, we can click on this paper icon. And again, it tells us the long name, which is surface potential temperature. And it tells us the units, degrees Celsius. If we click on this little cylinder icon, it gives us the graphical representation. And here we can see that now it's a 3D variable. So we've got time. That's what this 14,965. It's a lot of time steps. And then we also have longitude and latitude. And you can see this is the variables are much larger. So each variable is about 520 gigabytes. When you got 12 variables, that adds up pretty quickly. So that's a very big data set. Okay, just going to zoom out a bit. The last thing that you have is these attributes here. These are a bit different depending on the model, but these can have some useful information for you. For instance, this says for the calendar, this says all years have exactly 365 days. That's really useful to know if you're new to this model. We now have been told that there are no leap years because leap years have 366 days. So in this particular model, every single year has 365 days. So basically the attributes is where you can have notes, any kind of notes like that, that might be useful. And there are a bunch of other things here. Some of them are useful, some of them are less useful for us. but useful for some of the people who made the data set. So that's a lot of information. But you can see that all of this information that I just went through, so the attributes, the dimensions, the coordinates, and the variables are all kind of clumped together within the data set. So they're all within that DS data set that we loaded in. And that's really where Xarray is really helpful. So instead of having all of these data variables in different files and having to load them each in separately and put them all together, it can consolidate everything into one data set and store it all together. And everything that I've showed you here is not actually the data. So we haven't seen any actual numbers yet. So there's nothing here that said SST at, this location in the ocean is 15 degrees. Like we haven't seen any actual data yet. All we've seen is the metadata. And so we call that metadata when it's kind of explaining the data. So the names of the variables or coordinates, the dimensions, the size of each of those things. So when we load a data set in Xarray, this is what we mean. We actually only load the metadata. So no actual data has been loaded yet into the computer. Okay, this is a lot. Are there any questions, or is anyone just completely lost yet? Please don't be shy. Nope. Okay, so I guess either you're all following along or I've lost you all. Hopefully the former. Okay, so what I just said is all listed here as well. So you can read through here. Hopefully this is somewhat helpful. But so now we know how to, if we just type DS, then we can view all of that content that I just showed you. But let's say we are just interested in sea surface temperature. Oh, sorry, I just saw a question. Do we have 4-dimensional data? So here we actually, that's a good question. In this data set, we do not have 4-dimensional data because none of these variables, we can see the data variables listed here. Close these. All 12 of these, you can see that they all have 3 dimensions. So time, latitude, and longitude. So in this case, they're all of the variables are 3 dimensions. And that is because this data set on the cloud is just for the ocean surface. So that is a good question, but in this case, we don't. But everything I've said here would be completely identical if we did have 4-dimensional data, and it would be 4-dimensional if any of these had a Z or a depth dimension added. So that was a good question. Okay, so let's say that we're just, oh, yes, question? Sorry, was this a question for me? No. Okay. Cool. Just a reminder to mute if you are attending and not asking a question at the moment.
Good morning. Leave me alone, Jerry.
Okay, I'm going to mute you, but as always, you're welcome to unmute if you have any questions. Okay, so if we're only interested, or we're interested right now in the variable SST, then we can access that by saying ds dot. So we're accessing something from the data set. That's what the dot means. And we're accessing the variable SST. And if we just type that and evaluate this cell, then we get some information about it. And now we can see that this ds.sst, the type of that data is an Xarray.data array. So this is a bit different. when we just typed DS up above, it was a data set. Whereas here we have a data array. And a data array is just a single variable, whereas a data set is a collection of all of those variables and everything from before. So in this case, it's a data array that's called SST. And then we have all of the dimensions listed here. So we have time, latitude, and longitude. And we can see this, which we actually saw up above when we clicked on the little icons. We got this same thing. So this is actually no different from the information above. It's just selecting out the sea surface temperature. But we don't have to do that. So from the data set, we had variables, but we also had dimensions and coordinates. You can also access those by saying ds dot whatever dimension or coordinate you want. So here I say ds dot time, and we can see what this is. So this is another data array. It only has one dimension because it's time. That's all we wanted. And here we see that this is using a specific date format, basically, which is called CF time. And we can see that it's using this date time no leap. And that's because, as we saw before, there's no leap year in this data set. So this is just a way to kind of view what's going on here. You can list all of the dimensions by saying ds.dims. Then you get a list like this. It doesn't look quite as nice as our what it looked like above when we when we just typed ds and we had the nice representation, like a graphical representation. But this is how you can kind of access any of these things. So if you are interested in selecting only a specific range or a specific value in your data set, you can, so let's say we're still working with our SST, but let's say I only want the sea surface temperature, SST, at one time step, and I just want it at the first time step. And remember that Python starts indexing at 0. So when I want when I say the first time step, what I really mean is the 0th time step. So I'm going to say time equals 0. So I would do this same thing, ds.sst. So I'm grabbing the SST variable from the ds dataset. Then I use this .icell function, which is selecting the data using the index. So that's icell. And then you can say whatever dimension you want and whatever index you want. So you can say time equals 0. And let's see, if I evaluate that cell, what do I get? So now I get, yet again, it's a data array, but now notice that there's no time dimension here. Whereas before, when we said ds, where was it? Up here, ds.sst, we had time, latitude, and longitude. We've gotten rid of the time dimension because I said just grab one time point. So now we just have a 2-dimensional array of latitude and longitude. That looks like this. If you wanted to select a range, so if you wanted to select more than one time step, you can use the slice function. And that basically just means slice the data set in this range from 0 to 10. So now we're taking the first 10 values of time. And so if I evaluate that, the time dimension should be 10. Yep. So now we have a time dimension of length 10 because that's all that I asked for. Let's see. There is a question in the chat. So that, I think that's a very involved question, probably. so what I can say is like, you're absolutely welcome to use any of the cloud data sets to do research. Definitely. So I actually am not a super expert. Joseph might know a bit better, actually. I think if Joseph Ansong is on here, about which ocean data sets are better to use for different types of research. And that might be a really good conversation to have. I won't go into that right now, but you're absolutely more than welcome to use this data. It's here to be used, and it's used in a lot of publications and presentations, and you're absolutely welcome to use it. In the POP model, do we have a SALT budget terms? Ooh, I don't know about the SALT budget. It does have, just scroll back up. So when I printed out my DS data set up above, I can go down to data variables and I can take a look, and there's SSS. And if I click on this, it will tell me that's surface salinity. So you do have surface salinity in this model. If you're interested in the details of the models that are on the cloud right now, I'll show you this again. I suggest going to the Pangeo data gallery. If you go to pangeo.io, which is a great website, and then you go to site and you go down and click on Pangeo data catalog. You click on catalog over here. Sometimes this can be a little slow. And then you can browse the master catalog and you can search this way. So you can click on any of these and you can see, you'll actually see what variables are available in each of these things. And you'll actually notice that how you're viewing the here on this website is using the Xarray output. So it's actually the same output that we're viewing everything in now. So this looks exactly the same as what I was just looking at. So you can take a look at all of these things. Yeah, great. Thanks, Joseph, for jumping in there. And to Amemu, yes. So using iCell is a way for you to reduce the dimension. Reduce dimensions or reduce the size. So you're saying, oh, I only want 10 time steps instead of 14,000 or whatever we had to begin with. So yeah, absolutely. There is another, actually one of the ECCO tutorials has this. You can use just a regular .select, .sel. Let me zoom in. So instead of saying, so the iCell means that you're putting in an index. So here I said time equals 0 because I want the first time. You could also just select like this, so .cell, and then you would want to put the actual value of time here. Time is a bit confusing because of the datetime formats. But if you had something like your latitude, I want, so n latitude is also basically an index. Well, this isn't a very good example, but that's another way to do it. And we'll see it in one of the we'll see it later. So I'll leave that until later. Okay. So let's say we are interested in not just picking out individual times, but we actually want to do a time mean. So maybe we have latitude, longitude, and time, but we just want an average over all time. And then we want to make a plot and a map of latitude, longitude. We can do that very easily by, again, saying ds.sst, and then we can just say .mean. And then here we just write which dimensions we want to average over. So if it's time, we put time. You could put n lat, you can put anything there. And if I evaluate that, you'll see that we again get this Xarray output. It's another data array. There's no time dimension here because we averaged over all of it. So now it's just 2 dimensions. so that's really handy to do. You'll also notice that this took almost no time to just say dot mean of time, whereas we had like 14,000 time points. And it's quite a large data set. This is a 10th degree model for those of you who know what that means. This is a huge data set. So to actually average over 14,000 time points, it would take a much longer time than it did. But the reason why it's so fast is because it didn't actually calculate the average. It just is saying this is how kind of Xarray works combined with dask, which we'll see in a minute, is it just shows you the metadata for the computation that you ask it to do. And then you have to actively say, now I would like you to compute this before it will do any computation. And again, this is a little strange to get your head around at first, I find, but this is what makes Xarray and dask so useful. Sorry, I feel like I'm getting some feedback. Because you have this, what's called like delayed computation, or what's called lazy computation, where nothing is calculated yet. It's just storing this so that when you say compute, so I could say something dot compute, and it would compute this for me, and it would take a really long time. Well, it would take a long time at the moment. So anyway, that's why all we're seeing when we're printing out this is just the metadata for what that result would be, but it hasn't actually been calculated yet. The other thing, if you didn't want to compute it, if you just say dot plot, if you plot anything, that will also trigger active computation. Sorry, I think I'm just going to mute one of you just because I've been getting a bit of weird feedback. I don't know if anyone else has. Oops. Don't seem to be able to mute that person. Okay. Sorry, if Seiki Wonder could mute themselves, that would be really helpful. Thank you.
And I think Amemu as well.
Okay. Yeah, thanks, Joseph. And again, you can unmute to ask questions, but if you could please mute in the meantime, that would be helpful. And thank you, Joseph, for answering some questions. Appreciate that.
You're welcome.
Okay, so here we go. So this is what I was saying before. So if we do dot plot, this will trigger a computation. And so here I'm saying dataset.sst. I'm selecting only the first time step. Otherwise, this would take a really long time. And I'm going to say plot. And I have a note here. This may take several seconds. So let's see. We can actually, this is a fun trick. If we put 2% signs and then time at the top of our cell, then it will print out how long it takes to evaluate the cell. All right, so that's going. We can see this star in the brackets here. That means that it's computing. All right, wasn't too slow. There we go. And there we have a plot. So this is sea surface temperature at the first time step in this data set. So we can see here that it gives us some time here, CPU time. So the most interesting one for us is wall time. Oops. Getting a lot of echoing today. Wall time, so it says 6.8 seconds. That's pretty fast. And that's how long it took to do this. Now you'll notice that all I did was say dot plot, yet I have a lot of labels here on my plot. And that's because Xarray has some built-in plotting functions for us. And actually the built-in plotting function here is using the pyplot library, which is what we saw yesterday. So it already labeled our X axis for us. It labeled our Y axis for us. The title is a bit funny, but it's telling us some of the coordinates, which is not super helpful in this case. But it also labeled our color bar for us and has a color bar. So it's saying surface potential temperature in degrees Celsius. So it's actually interpreting the metadata that's stored with this SST data set, SST variable. And so remember the long name said surface potential temperature. And then the units said degrees C, degrees Celsius. So it is able to interpret all of that and label everything for us. So that's pretty handy. All I had to say is dot plot. This is one line to select, one time step and to do the plotting, and it did all the labeling for me. So that's pretty nice. If you don't like the label, you can use what we did before. You can use pyplot and it will override anything that's in there. So you can still use your plt.title and change the title of the plot, for instance. Okay, and I'll just give another advertisement. So this is a map. It looks fine. It doesn't look great. If you want it to look great, you can use the Cartopy library, and there's a tutorial on that next Monday by Josue Martinez Marino, and he's quite excited. He's been preparing for that, so I definitely encourage you to attend that. Okay, so that's kind of just the overview of Xarray, and I realized that was a lot of information. Are there any questions at this point about Xarray? It's taking a while. I better hurry up if we're going to get to any echo. We might have to do echo tomorrow. But I think this is important. These are really useful libraries for this kind of thing. Okay. If there are no questions, I will continue on and we will move on to the library dask. And here I have a link here. So I said this is based on a dask tutorial. So again, like I said yesterday, you can always Google the libraries that we're using, and almost all of them have really good tutorials on their websites. And so I kind of took this one from, you can click here, from the official dask tutorial. So dask is quite a complicated library, but you can kind of roughly put it into two. It kind of does two different things. So one of them, there's a lot of jargon here, so bear with me. There's one, distributed computing for running code in parallel. So that basically means like parallel computing, if you've heard that. So running many different computations all at the same time, instead of running one computation after another. And that is very useful. That's kind of how we can do any of the computations we do with these large models. That's how we run models. That's how we analyze models. So dask helps us do that. It also has its own, so we saw that there were Xarray data sets and data arrays. There are also dask ones. And it's actually dask that allows us to do what I mentioned before, is this lazy computation or lazy loading, like I have here. And that means it's through dask that we're able to just load the metadata, and then we can type out the computation we want to do, but only when we say .compute. There's also a .load or .plot will we actually trigger any computation. So dask is actually what allows us to do that. So first, I'm going to talk about the parallel computing side of dask. So we're just going to do a very simple example. And we can see here that I'm defining a function. This is how you define a function in Python. So you say def, which is like define, and you have a function called add. And we're basically adding two numbers, x and y. Okay, I think there's a very specific question about salinity that I have to say I don't think I can answer in the chat. If anyone else is familiar with this, please do. But I myself have not really looked at salinity, so I don't know what PSS and PSU stand for. But as I said, you can kind of look through the models and figure out what's there. So we have this function that adds two numbers together. Return means that this is what if you run the function, it'll return something, and it will return the sum of x plus y. But it does something in between. And this is just so that this is just for demonstration purposes. You will never need to do this. Sleep of 2 means that I want this function to pause for 2 seconds. And that's just because adding 2 numbers is too fast. It's really fast. And so if we do any parallel computing with it, we won't notice because it's just a very quick computation. And now we're going to define another function that's called MLT for multiplication, where we multiply x and y. And this one sleeps, so it has this pause for 1 second in the middle. And you'll see why that's useful. So here we are going to run this cell. Remember, I had this % time up above, so that's how we can get the amount of time it takes to run this entire cell. And I'm calling it the add function once, and I'm calling multiplication twice. So the add function sleeps for 2 seconds. The multiplication sleeps for 1 second each. And so we would guess that the doing add once is 2 seconds, and then you add 1 second each for the other for the other multiplication ones. And so we would guess that this should take about 4 seconds. And let's see if it does. Oops, I didn't define, sorry, I didn't run this cell. So there you go, there's another error that says add is not defined. I said, well, that's weird, I just defined it. Oh yeah, it's empty here, I didn't define it before. That's where error messages are very helpful. All right, there we go. 4 seconds on the nose. So, so that's great. We just ran each of these things in series. So we ran this one, then we ran this one, and then we ran this one. It took 4 seconds. But with dask, you can speed this up where you could run them all at the same time. So we're going to import dask. We're using this delayed function. We don't use this delayed function as much, and we will use some dask later in ECCO, and you'll kind of see how we use it more often in like ocean and climate data analysis. But this delayed function, it's kind of what I was saying with the lazy loading. It's like delayed computation until you, for instance, call .compute. So if I go back up here, I just loaded the dask library and I just loaded the delayed function. Now I'm going to run this cell where the delayed function has been applied to each line. And I still have this time here so we can see how long it takes. So I run that cell and that took so fast. In fact, it took 758 microseconds. That's really fast. That seems a little suspicious because we know that even if we run these in parallel, the add function takes at least 2 seconds because we told it to pause for 2 seconds. So what happened here is what we saw up above. No computation has actually been done. All we have done is created this delayed or lazy computation. So now A, B, and C have been stored. And actually notice here I do, sorry, I should have mentioned this before. So the C actually depends on A and B. So I'm loading in the A and the B here. So if we go down below here, we can say c.compute, and that's when it will actually do the computation. And because C depends on A and B, then C has to wait until A and B have both run before it can be called. But A and B are both independent, so they can be run in parallel, which means instead of adding 2 + 1 for A and B, they'll be run at the same time. So we should just be adding, it should just be 2 seconds total. And then it will be 1 extra second to evaluate C, or at least that's what it should be. Let's see. Yep, so there we go. The wall time is 3 seconds. So here we've taken the same computation as we did up above, but above it took 4 seconds, now it took 3. That seems very minimal, but you can scale this up a lot and you can speed up your computation a ton, and you can actually make like these computations possible where they weren't possible before. So that's a very small example of how dask parallelizes our code. Now, the second part is that dask has these data arrays that works that you can work with them without Xarray, but most often we work with them within Xarray. So remember I loaded the data set DS before. I'm going
So,
to,
quick
yes,
question.
yeah.
Paige, before you go ahead.
Mhm.
So once you import dask, it knows automatically to parallelize your computations.
Kind of. So yes, in that it will parallelize things for you. So in this case, it knows. So when I run this cell here, it kind of creates a graph. We call it a dask graph. And it knows that A and B are independent and thus can be run in parallel. But it knows that C has to wait for A and B. So it will create like basically a parallelized graph, and we'll run it in what it thinks is the most optimized way.
Okay.
And for
Thanks.
very basic things like this, it works really well.
Mhm.
And it actually works really well always. But sometimes, it does something that's a bit funny if you have some really complicated computations. And then there are some tricks to kind of massage it to work a bit better. But yeah, for the most part, it really knows.
Okay.
Yeah, that's kind of
Thanks.
what's so great about it.
Yeah.
Theoretically, I think the idea is that you don't have to know how to parallelize the code at all. Just run it and it will do it for you.
Right.
That's the goal.
Thanks.
Yeah. Okay, so I just evaluated this cell again. And this is the same thing we saw up above, where we have a data set that has dimensions, coordinates, and data variables. So if we look at the data variables, so remember we looked at SST before. If we move over here, we actually see that this says dask.array. And that's because the SST, even though it's an Xarray data array, which we saw before, it's actually Xarray wraps dask.array. So basically, in this sense, Xarray is a wrapper over dask. So the dask array, it's actually a dask array at the core. It has a chunk size. You'll see this a lot because in order to make the dask work well and how to work with large data sets, everything gets chunked into smaller kind of like bite-sized chunks. So anyway, that's the other thing that dask does, is it provides kind of this delayed or lazy loading and computation, and Xarray wraps around that to provide all the metadata to go along with that. So that's dask in a very, very small nutshell. But dask is very powerful, can do a lot of cool stuff. I'm still trying to understand how it all works. It's pretty complicated. But basically, because of especially these two libraries, we are able to analyze, large amounts of data with minimal effort, usually, in a small amount of time. And that's really, really amazing and kind of revolutionizing how we can do our data analysis. Okay, any questions on all of that? If not, I'm going to jump quickly over here. So this session was supposed to be about ECCO, and we've just spent the first hour going through Xarray and dask. But all of this is based on Xarray and dask. Xarray wraps dask, so we're always kind of using dask in that sense. So this website here has a lot of information about ECCO and all things Python analysis related with ECCO. So it's a good resource. I'll post this in the chat right now. I can post it in Slack later as well. It has all sorts of information about ECCO and how it all works. Now, the only difference is that here it will tell you how to access the data not from the cloud. Whereas in our Jupyter Hub, we can access it from the cloud, which actually makes some of these steps much easier. But one of the tutorials that I actually just updated today. So it's a new one that you might not have seen before, but you all should be able to see this. ECCO example calculations SSH, so that's sea surface height. That is adapted from one of the tutorials on this page here. And we will be making use of this Python library. So it's echo_v4_py. And that is a package built specifically for doing computations and plotting with Echo, which is really handy. It has some really nice information here, most of which I've already gone through, so I actually won't go through this. But for instance, this is talking about how the data is stored in Xarray, which is what I just went through. So remember we had, oops, I can't highlight. Remember we had this data set, like an Xarray.dataset. So this is basically saying within that data set, it points to a bunch of different things like your dimensions, coordinates, your data variables, and your attributes. So this page is quite nice. This is under Echo data structures and kind of explaining in more detail what I just went through. And that's how everything is stored in any data set that we load with Xarray. It will have this format. Now, very briefly, I don't know if we'll get to the grid specifically, but this was mentioned by someone earlier, the Arakawa grid, an ocean model, and hopefully you've all seen Joseph's ocean modeling videos and notes, like some lecture slides, and they do mention this. So you basically have to discretize because we're in a, well, to model it, we need a discretized world, basically. So we discretize our ocean, and we have what's called, usually we use an Arakawa grid, and Echo uses an Arakawa C grid. And that basically means that you have different data variables are stored at different points on the grid. So here we have this middle point C. That's where things like SST, so like temperature is stored. But these U points, these green ones, are the zonal velocity, and V is the meridional velocity. So I'm not going to go into more of that at the moment, but there is one of the tutorials mentions the C grid, and so that's kind of what we mean by that. And if you have questions about that, I recommend attending Joseph's sessions and watching those videos. Those are quite nice. Okay. So let's start with this one. Sorry, it's very dry in winter here. You drink a lot of water. Okay. So we have about 20 minutes, and I will have to go right on time. Oh, sorry, I have a tickle in my throat. Okay. So this example is taken from the Pangeo gallery page, which I've shown in some previous sessions. And I just tweaked it a bit for us, but mostly it's from the Pangeo gallery page. And we are going to, so in this case, I'm actually not going to use the Python package that I just mentioned. We do in the other one, so you can take a look at that. In this one, I don't. I think part of that is because this was written before that package was out, and it kind of incorporates some of it here. But the other thing that's a bit funny is that when the data is transferred from the NASA servers, which is, I think that's where Echo is being stored, onto the cloud, some of the names of, for instance, dimensions got changed. So anyway, it was easier to just keep this as is. So we're not actually going to use that library at the moment, but we can still do a lot of analysis with this. All right, so we're going to start by loading in the data from the cloud. This should look very familiar. In this case, I'm loading in ECCO version 4 instead of the CESM pop model, which is what we did in the last one. So if I evaluate this cell, I still am calling my data set DS, but in this case, our DS is ECCO. But we have, sorry, I'll zoom in again. We have everything written out the same way. So we're starting to see some things that look familiar. So we have dimensions. In this case, we have very different dimensions than in the previous data set. So we have this thing called face that will be clear what that means later. We have I, and I is our index that's kind of in the X direction. J is in the Y dimension. And then we have these other ones, IG and JG, and those are some of different, when I said that we had the Arakawa C grid where some of the data variables are offset from each other, that's why we have a separate X and Y index, because you have some data that's offset. K is the vertical dimension. And so you have similarly a bunch of other K dimensions. And then you have time, and there are 288 time steps. I believe this is monthly data, whereas the previous one was daily, which is why we had like 14,000 time steps. So we can look at all the coordinates. Again, like as I said, I'm actually quite new to ECCO. So a lot of these, like depth is pretty self-explanatory. We can click on that and it says ocean depth. Well, that seems pretty obvious, but some of these may be less obvious. So one that we're going to look at later is HFAC-C. And if I click on that, it says vertical fraction of open cell. So we'll look at that later. I won't talk about it now, but anyway, this basically tells you, it kind of tells you what it is. Maybe it doesn't. It's not all the information you need. But ECCO actually has a lot of it has really good documentation. And that's where going somewhere like this is a really good idea, because it has all of the information you need. Okay. So now we have loaded, and of course, when I say load, I mean that we have loaded all the metadata using Xarray, the data set. Now this is kind of fun because I was curious how big the data set is. And you can use that by saying .n bytes, so like basically the number of bytes. And then I divide by 10 to the 9 so that I can get the result in gigabytes. So if I evaluate that, we get 150, almost 153 gigabytes. So this data set is 153 gigabytes, which is actually kind of small for compared to some of the climate models, like the last one that we had, where each of the 12 variables was over 500 gigabytes. But 150 gigabytes is still pretty big. That's a lot to have to analyze on a local computer. So anyway, so we'll move ahead with using some Xarray and dask. So we'll start with Xarray, which we've already been using. This is just, a trick to make things work faster. We're basically getting rid of some of the coordinates here. We had more coordinates up there. It's just, something you can do if you don't need all of those coordinates, which in this case we don't. Okay, so now we want to visualize the data maybe. So we just want to see what it looks like. And we will see how it looks. So going to run that cell and we get something that looks like this. And you see that it's kind of it has these different tiles. So that's what this face dimension is. There are 13 faces, so it goes from 0 to 12, that are actually called tiles as well. It depends on where the data is saved. It's a bit of an annoying feature. But it doesn't really look like the globe as if you were just plotting it like this. And here I'll note that we're plotting the depth of the ocean. So I just said, I want the coordinates. So access the coordinates dot depth and just plot that. And here it's a bit fancier because we're saying we want to plot each of the faces separately. So yeah, this looks a bit odd. And here is where we are going to use Cartopy here to make it look nicer. So we're going to start using Cartopy, but I will not go into the details. In fact, all of this was written ahead of time, and I'm not going to go into it. And all of this is included in the Python Echo Python package. But for now, I'm just going to run that, run this cell. And this is basically, it's called a class. It's basically like a function. And now we can use that to make our plots. And this basically, what this class is doing, or function, is it's stitching together all of the faces into something that looks like a map. So now if I run this, whoops, NP, okay, so here we have another error. Name error, NP is not defined. So it means that this was expecting me to have loaded NumPy. Let's see, was I supposed to have loaded NumPy? I was. Looks like I didn't evaluate this top cell, because if we zoom in, it's this is empty. So I forgot to evaluate this cell. So now that I evaluate this, now we have NumPy is loaded as NP. So now hopefully it should work. Good example about how error messages are really helpful. And run that. And there we go. Now we have something that looks much nicer. We can actually interpret it as a map. Cool. And for some of these things, as I said, the Echo Python package can do this as well. But you can also just copy and paste this and use it yourself. So you don't necessarily have to know how to do all of that, what's in that function, which is why they create libraries like the Echo Python library. Okay, so let's select some data. So this is basically putting into real practice what I was showing before in the little Xarray tutorial before. So now we're going to select, now we're going to use theta. If we want to know what theta is, we can again go back up here. We can look in our data variables and we can say, let's see, oh, here's theta. What is theta? Click on this. It's our potential temperature in degrees Celsius. So this is basically the same as what we had before, SST, except that this is temperature, not just at the surface, but at depth. And that's because it has this K dimension. And we can see the size of theta if we'd like. So here, because we have, so here's an example of a 5-dimensional variable. And that's because it has all of these different, so, well, okay, let's go through it. So it has 288 time steps. It has 50 vertical layers. So that's K. Then for face, it has 13 faces. And then the J and the I, so the 2 horizontal X and Y dimensions have 90 points. So that's why this is a 5-dimensional variable. And that's very hard to represent. We can't actually represent that. So instead, we get this representation where we have 2 dimensions listed here and 3 here. That's how they represent 5 visually. Okay, that was a little side note. Let's go back down. Okay. So here is where we're going to use an example of cell. So we're selecting, but not using an index. Instead, we want to use time. So here we can select a specific time. So we want to say we want theta. So we want the temperature from January 15th, 2000. And we want it at K, so that's the vertical index, equals 0. So K equals 0 means it's at the top. And then we type SST so that we can print out the information. And here we go. So we get this Xarray data array representation again. Now it's theta, and we see that now it's only 3 dimensions. And that's because we took 1 point in time and we took 1 point in the vertical. So now it's only 3. So we have this face, and then we have horizontal and X and Y dimensions. So again, we can look and see what all of this stuff means, but we've looked at some of those before. And here, this line is kind of stressing what I've mentioned several times now. So no, we haven't actually computed everything. So we've selected this, but it's just showing us the metadata of what this selection would look like. But if we say .load or make a plot, then it will actually load. So here, if we pull, this is our mapper function from above, then we can plot the sea surface temperature. And this is just saying which color map to use. So we can run that. Cool. So this is showing sea surface temperature. And again, it's labeled theta with degrees Celsius. And it looks pretty nice. And this is using Cartopy. That's why we have this really nice projection, and all of the continents, the land is covered in gray. And you can learn more about that on Monday. Any comments, questions for now? We have a few minutes left. No? Okay. So I'll just keep going so you get to see kind of more examples here. So now we can do some calculations. So again, we're putting this, our kind of sample data from before, we're actually going to use it for the ECCO. So I'm going to say mean SST. So now we want to take the time mean. So I do what I did before, ds.theta, select k equals 0. And then I'm going to say dot mean dimension time. So we've seen that before. And if we print mean SST, we see it happen instantaneously. And that's because no calculation was actually made yet. But we can do this here by saying dot load. And here we're using a different trick, which does the same thing as before. So if you just use 1% sign and then type time space, then it will time however long that line of code takes. So instead of the whole cell, it's just that single line. So I will evaluate that. And we'll see how long it takes. And it will tell us because we have this percent time. And we have this note here, but it does take some time. So we'll see how long it takes. So I feel like there are a few questions here about what variables these different models have. I actually think that ECCO does have, I know the heat budget a bit better. I actually don't know the salt budget. All right. Gonna have to mute you, Emmanuel, because it was very noisy. So I think that ECCO does tend to save all of the variables needed to close a heat budget. I don't know about the salt budget. I would guess probably, but I don't know. You're going to have to look at that yourself. Maybe Joseph knows, or if not, Dimitri would be a great person to ask. So I'd encourage you to go to his Q&A next week.
Yeah, Dimitri.
Yeah, cool. Okay, so we can see here it took 35 seconds. And now we see a different representation. So it still says xarray.data array, but now we see a bunch of values. So that means that it actually loaded, that's why we said dot load. It loaded the mean sea surface temperature. So notice there's no time dimension here because we took the mean over time. So now we just have, well, these 3 dimensions. And now we can do this plot and we can see what the mean sea surface temperature is. And you'll notice that it was very quick to make this plot. And that's because we called mean SST here, but we have already loaded it here. So it didn't have to recompute it to plot this time, because when you say, when I did mean SST.load, it means load mean SST and save it as the variable called mean SST. And so that's why it was really quick to load. Oops. So anyway, this is the mean sea surface temperature from ECCO. I forget how many years it is. It's something like 23 years or something. Okay. So I have about 5 minutes left. Does anyone have any questions? Do we want to have a little question time, or should I try and get through a little bit more? Any?
So, the motherboard is right?
Sorry, Rex Henry, could you repeat that?
Sorry, no question. Sorry.
Sorry, I can't understand what you're saying. It's very, I'm getting a lot of noise when you speak.
It's a mistake, sorry. It's no question, sorry.
Okay, cool. That's fine.
Yeah.
Okay, well, if there aren't questions at the moment, I'll just see if we can get through this. It sometimes takes a couple minutes to spin up what's called a dask cluster, but we can go ahead and start. And we just might have to bail partway through because I have to go in 5 minutes. So we're speeding things up with a dask cluster. So this is kind of what we saw before, where dask can be used to parallelize code. And we're going to do it in a much fancier way now than before. So before we used this function called delayed. And as I mentioned, we don't really use that. I mean, that's the basic, that's kind of the basis of what we use, but it's much more complicated. And on the cloud, we use something called dask gateway. You don't really need to know that, except that if you hear it, that's what we use on the cloud. And it's dask distributed. So there's a lot here. I won't go into this too much, but this is, you can basically copy and paste this if you want to start a dask cluster. And that is how, once a dask cluster is running, anything that you run from Xarray or dask will be run on the cluster, which allows for parallel computing. So if I shift return and or shift enter, and that can take a bit of time. So we'll see that spin up. And then we're going to do, once that's spun up, we will run the same thing that we did before, where we take the mean over time, and we're going to see how much faster it loads. Hopefully it loads faster. Okay, so we now see that this, it now says 14, so it means that the cell ran. But in this case, we're not ready to go yet. But we do have this nice interface here with our cluster. And this will update in real time to show us when our when our dask cluster has started. And so dask cluster is basically when you get a lot of kind of CPUs to run your computations. And it can take a little time to spin up. It depends on a few factors. If this will take, this can take a couple minutes sometimes. But you know that you are ready to go when these numbers here no longer say 0. And so that's workers, cores, and memory. And so this is basically telling you how much like CPU power you have, and then how much memory capability you have. So hopefully this will spin up. If it doesn't spin up in the next 3 minutes, then we will have to start here again tomorrow. So the other thing that you can do, and is there's this dashboard here, and you see that this is actually a link. So it won't show anything at the moment because it hasn't spun up yet, but I can click on this link. It opened in a new tab. And this here is a dask dashboard, and it's how you can watch your computations being computed by what we call the workers, and basically by the CPUs. And so you don't see anything here at the moment because the cluster hasn't started up yet. But once it starts up, then you will start to see a bunch of bars. And to be honest, it's going to be very confusing at first. So I'm basically just mentioning it as knowing that it's there, and can provide a lot of kind of links to other places you could go to read more about the specifics. But it doesn't look like it's going to start up for us very quickly. which is a bit of a bummer. Okay, well, any other, so there's, and sorry, I hope I'm getting the name right, Ogunseetitus. Sounds like you're interested in doing some ocean modeling.
Yes.
Yeah, cool. Hopefully, there might be some other people here who are also interested. And yeah, maybe we could, put together a small group to kind of work on this stuff. Oh, it started up. So now we have workers 2, cores 4, and we have memory at just under 9 gigabytes. Okay, so anyway, it started up. If we go over to this tab, we can now see, oops, there was a little line there for a moment. Yeah, this blue line, but no computation is being done at the moment, which is why we don't see anything. All right, I'm going to evaluate this, which is the same thing that we calculated before, which is the time mean. Up here, our mean SST. And I will start that. Let's go over to this tab, and we now see that things are happening. So this is a representation, a visual representation of our computation being done. And all of these bars here, so these are all workers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All of them are running at the same time. So that's kind of our computation running in parallel. And you can see that there were that many, these are actually the number of cores, because we have 2 cores per worker. So there are 5 workers, 10 cores. Doesn't really matter at the moment. And this ran in 13 seconds. Whereas when we ran it previously, it ran for, what was it, 35 seconds? 35 seconds. So we just sped up our time by a lot, more than half, almost 3 times. So that's a demonstration right there of how dask can speed up your computation. And again, when it's only 35 seconds, not a big deal. If it would be 30 hours and you can change it to, number of minutes, that makes a really big difference. So I'm gonna have to stop there today. Hopefully that was somewhat helpful. I really encourage you to, take a look through this again, kind of go back over what we've looked at. Maybe take a look at the Xarray and dask tutorials that I linked to in the notebook for intro Xarray and dask. And feel free to come with any questions. Tomorrow, so we're doing the same thing tomorrow. We have 2 hours. So I'm probably going to try and go quicker so we can get through more of the actual ECCO content. And then I have a Python Q&A next Wednesday where you can ask questions about any of this stuff. Okay. Thank you all. Thanks for joining. Hopefully, even if you couldn't quite follow along all of the individual steps, you can see just how powerful some of these libraries are, and yeah, how, with some practice, you could be doing some big computations too. I think someone asked how to get the recording. I'll be posting it in the Slack channel, which is Python 2021. So please make sure that you're on there, and that's how you will get links to all of the YouTube recording. Okay. I'm going to have to say goodbye. Enjoy the rest of your day. Let's see what you have. I think you've got, yeah, no problem. You've got graduate school paths panel from 3 to 5 today. I think that's the only other synchronous thing going on.
Okay.
All right, well, hope
Thanks.
to see you tomorrow. Yeah, thanks, Joseph, for your help as well.
Yeah, thanks, Paige.
I hope
That
this was
great.
somewhat helpful.
Yeah, it was great.
Yeah, cool.
Yeah.
All right, bye, everyone.